So our next graph we're going to take a look at is the natural logarithm function. And the equation for it is f of x equals ln x. Okay, so for this graph, it is going to be a continuous graph. Okay, there is a horizontal a vertical asymptote here, but because the only graph that we're looking at in its domain here is here, it is continuous on its domain. So this is considered continuous. Okay, so odd, even, or neither. So it is not symmetric about the y-axis and it's not symmetric about the origin. So it's going to be neither. So if we look at the domain, so for the domain, looking at our x values, so there are no negative x values, and because there is a vertical asymptote here, it's going to get really close to 0, but it's not going to touch 0. So it can be anything bigger than 0. So since it can't be 0, we're going to do parentheses 0, and then it can be anything bigger, so infinity. And then for the range, so we're looking at the y values. So going up in your y values, it can be any y value here. So the range is going to be all real numbers. Okay. So then we have our absolute value function, which is a V-shaped. And the equation for the absolute value function is the square root of absolute value of x, so it has these absolute value bars. And every once in a while you might see it say ABS of x, but normally it's going to have the absolute value bars around the x. So this graph is continuous, no holes or asymptotes there. Okay, so even, odd, or neither. So this one is symmetric about the y-axis. So this is going to be even. Also, if you did the algebraic test, if you plugged in negative x to the absolute value, that would make it positive x, so it would be the same as you started out with. Okay, so then for the domain, so the domain, looking at our x values, it can be any x value here. So from negative infinity to positive infinity. And then for our range, so for our range here, if you notice there's no negative y values. It can be 0, and it can be 0 or anything bigger than 0. So 0 is going to be included, so it's going to get a bracket, so from 0 to infinity. Okay, next we have this greatest integer function. So a little strange. So the greatest integer function, it says int of x. Normally when you see this greatest integer function, it's going to have brackets around the x. So those both mean the same thing. Those are the greatest integer function. So what it is for the greatest integer function, so let me kind of explain. If I asked you the greatest integer function of 2.5, well, the greatest integer in 2.5 would be 2. If you look at the graph, if we're at 2.5, if you're anywhere between 2 and 3, it automatically puts you at 2. So if I ask you like the greatest integer function of 4.1, well, here's 4.1, that's automatically going to put you at 4. Okay, so these are jumps here, and they do have some of the holes at the next level, but they are jumps. So this is not going to be continuous, it's going to be discontinuous. And because we have the jumps, remember jumps are non-removable. Okay, so when we're looking at the domain here, you can plug in any number to find the greatest integer of it. So the domain could be any number, negative infinity to positive infinity. The range is strange, and you can't write an interval notation. So if you notice, the range could only be these integers. Okay, so the range, you would just have to write all integers. So there's no way to write that in interval notation. Alright, so that's called the greatest integer function. So then we have the logistic function. And it has a little strange formula here. F of x equals 1 over 1 plus e to the negative x. Okay, so it looks kind of like a rational function, but also has e in it. So that's called the logistic function. So what's going on here is you do have horizontal asymptote here, and you have a horizontal asymptote here. Okay, so it is going to be continuous for the graph that we're given. So it is continuous. Alright, so if we're going to look at the domain, so the domain is our x values. So you can plug in any x value. As you can see from here to here, it can be any x value. So from negative infinity to positive infinity. The range, looking at the y values, so it can go from 0 and it can go up to 1. But it doesn't touch 0 because of the horizontal asymptote, and it doesn't touch 1. So it goes from 0 to 1, but they're both going to get parentheses. Okay, and then we have the sine function, which you should have talked about before. And that is f of x equals sine x. Okay, so for the sine function, this is a continuous function. It keeps going on, no holes, no asymptotes there. So even, odd, or neither. And I forgot to mention on the other ones, but even, odd, or neither. So this is going to be symmetric about the origin here. So this is going to be an odd function. Okay, so when we're doing the domain, that is the x value. So as you can see, it can be any x value here. So the domain is all real numbers. But then when you're looking at the range, so our y values, the lowest it goes down to is -1, and the highest it goes up to is 1. Now it can touch -1 and it can't touch 1. So it's going to be bracketed as -1 to 1. Okay. And then our last function is our cosine function. And it is f of x equals cosine x. It's very similar to our sine function. The only thing that's different about the sine and the cosine function is where it starts. So cosine starts at the max, whereas cosine starts at it's called the midline. Okay, so for the cosine function, it is also continuous. Now the cosine function is symmetric about the y-axis, so it is going to be even. So when we're looking at our domain, so it can be all real numbers for the domain. It can be any x value. And then for the range, same thing as sine. So it can go down to -1, up to +1. And it can be -1 and 1, so that you're going to get brackets. Okay, so the last thing I want to do is just go back and talk about if things are bounded. And I'm going to go backwards just because we're here. So remember, functions are bounded. If you could draw a line on top and bottom, it's not going to cross. And we're just going to talk about just bounded in general for both. So cosine is going to be bounded because it will never touch a line up here or up here. So this is bounded. And then the sine function, same thing. If you draw a line on top or draw a line on bottom, it's not going to cross, so it's also bounded. So if we look at our logistics function here, this one is also going to be bounded because it already has those asymptotes, but it's never going to cross anything higher or lower than that. I didn't talk about odd or even for logistics, but it's not symmetric at the origin, and it's also not symmetric at the y because it would flip over here. So that's neither even or odd. And then our greatest integer function, so this will keep going up forever and keep going down forever, so it's not going to be bounded. So I'm not going to write anything for that. And then this one is also not going to be symmetric, so it's not going to be even or odd. And then if you go back to the absolute value function and the natural log, so this one will be bounded below, but not bounded for both. Okay. And then over here, this one would only be bounded, this one wouldn't be bounded at all, because it would cross. And if you go back to the ones that we looked at the beginning, so for the identity function, this one would not be bounded because it would cross. The squaring function would be bounded below. Our cubing function would not be bounded because it would cross. Reciprocal function would not be bounded because it would cross both. And then our square root function it would be bounded below because it would not go any lower than that. And then our exponential would also be bounded below, but not above. So the only three are the three ones at the end that would be bounded in the above and below. So our logistic, our sine and cosine, those are the only ones that would be bounded above and below.